Hello and welcome to the talk on scalable ML workloads using PyTorch. My name is Geeta Chauhan and I lead the Applied AI group at Meta AI. I will start off by giving you an overview of why we care about large models, challenges for training models at scale, and then dive into features in PyTorch distributed that help you with scaling. I will also describe the experiments and key insights, and finally go into the profiling and troubleshooting aspects for large-scale model training. During the last 3 years alone, model sizes have grown 10,000 times from BERT with 110 million parameters to Megatron 2 with 1 trillion parameters, and this trend is only going to continue further. Numerous studies have shown that the accuracy of deep learning models improves smoothly with increasing model size, dataset size, and amount of compute used for training. Sampling efficiency of large models is also better, resulting in same performance with fewer optimization steps and using less data. One good example is the Meta AI few-shot learner model, which we use for hate speech prevalence. So here it is able to correctly detect posts versus the traditional systems which were not able to successfully analyze these before and help reduce the prevalence of harmful content on our platform. It does this by proactively detecting potentially harmful content and preventing it from spreading on the platform. Meta AI few-shot learner is a large-scale, multimodal, multilingual, zero or few-shot learner model that enables joint policy and content understanding, generalizes across integrity problems, and doesn't require model fine-tuning. Few-shot learner can adapt to take action on new or evolving types of harmful content within weeks instead of months. As part of Meta AI's commitment to open science, we recently shared the Open Pre-trained Transformer, the OPT 175 billion parameter language models, along with all our nodes. We invite the research community to sign up and get access to these models. This is for advancing research in responsible large language model development. We also published our work on the 1.1 trillion mixture of experts models trained on Azure. Even with the most advanced compute hardware, training models with 10 billion plus parameter requires multiple GPUs. And training models with 100 billion plus parameters requires several multi-GPU nodes. Compute and memory resources are finite, and scalable distributed training that can generalize across a wide range of models is hard. It requires software tools that are user-friendly and make it easy to scale models with few lines of code changes in an efficient manner. This is where PyTorch Distributed comes in. The PyTorch Distributed stack provides features that facilitate training models in distributed systems. It includes a number of composable primitives like the communication collectives, the remote procedure calls for distributed model parallel training, and we are soon adding support for sharded tensors. There are many ecosystem solutions built on top of PyTorch Distributed, including Microsoft's DeepSpeed, Megatron LM from Nvidia, FairScale library from Fair Research, and the SageMaker model parallel from Amazon. PyTorch Distributed provides native package solution for DDP with communication compression, fully sharded data parallel, and state sharding, pipeline parallelism, and we are adding support for more tools for model parallelism. Usually, distributed training can be categorized into data parallel and model parallel. PyTorch Distributed Data Parallel trains models in each device independent from different batches of data and synchronizes the results at the end of each training iteration. The synchronization is built on top of collective calls. Model parallel is a process of splitting models across multiple devices and creating pipeline computation to train models across devices. This is usually used for when models are too large to fit into a single device. For communicating results across multiple machines, RPC or point-to-point calls are used. In this talk, we will focus on the new features for FSDP, DDP, and pipeline parallelism. Depending upon the size of your models or the domain, different techniques will be more applicable. For example, DDP works well for models less than 1 billion parameters. FSDP gives good results for models ranging from 100 billion to 1 trillion parameters. And combination of DDP and pipeline parallelism gives good results for models between 1 billion to 100 billion and the larger dense models. Sharded and RPC techniques work well for large embeddings and large graph models. The mixture of experts gives good results for large sparse models greater than 1 trillion parameters. So let's look into the three main techniques for distributed training. First, distributed data parallel or DDP is the vanilla data parallelism technique. You can see that the sample code on the right, here one wraps the model with DDP call and the rest of the training is similar to local model training on your local machine. With DDP, each process holds a full copy of the entire model. During initialization, the rank 0 broadcasts the parameters to all the other ranks to make sure training starts from the same state. Then, in the forward pass, the DDP will use the user-defined forward function and run it locally on the local device. And in the backward pass, the gradients are synchronized across all ranks using the all reduce. Next, the fully sharded data parallel or FSDP. It is inspired from Microsoft's DeepSpeed 03 and the code is upstreamed from Fairscale's FSDP. The code is shown on the right. FSDP is a type of data parallel training, but unlike traditional data parallel, which maintains a per GPU copy of the model's parameters, gradients, and the optimizer states, FSDP shards all of these states across data parallel workers and can optionally offload the shared model parameters to CPUs. You can wrap your model with FSDP and rest will be similar to local training. One caveat is that please use FSDP model parameters instead of original model's parameters to initialize the optimizer because each process will only keep shard of the model parameters. That's why the original model's parameters might not work. Usually, model layers are wrapped with FSDP in a nested way, so that only layers in the single FSDP instance need to gather the full parameters to a single device during forward or backward computation. The gathered full parameters will be freed immediately after the computation, and the freed memory can be used for the next layer's computation. In this way, peak GPU memory could be saved and thus training can be scaled to use a larger model size or larger batch sizes. To further maximize memory efficiency, FSDP can offload the parameters, gradients, and optimizer states to CPUs when the instance is not active in the computation. This is auto-wrap policy argument in the constructor that tells FSDP how to decompose into smaller FSDP unit. It can be based on number of parameters or any user-defined criteria. We need it because within each FSDP unit, it will run all gather to collect full parameters before computations and then discard them afterwards. So if there is only one FSDP unit wrapping the entire model, it will collect all parameters and that won't save any memory. You can see how the auto-wrap is structured by simply printing the model. And this is a very helpful technique that you can use for debugging issues like the case when entire model is packaged into a single FSDP unit. Here is a code snippet of how to define the policies for CPU offload and backward prefetch. And here is an example of policy for doing the fine-grained mixed precision control. Next is the pipeline parallelism. Today, it supports only single machine multi-device. The distributed version with support for multi-host is coming soon. This has been inspired by gpipe and the implementation has been upstreamed from the torch pipe repo. Under the hood, pipeline parallelism places each submodule in the input NN sequential on different devices. The structure of the input NN sequential dictates how models are partitioned. The argument chunks in the constructor determines how many micro batches it should split one mini batch into, and it will fit micro batches in the model in pipeline fashion. Since both model and activations are partitioned across multiple devices, it can also support larger models, but at the cost of more GPUs. In terms of the API, it only supports NN sequential as the input model, so one may have to modify the model source code into the structure to use pipeline parallelism. Rest of it is very similar to the local training. If you have access to the model source code, it won't be too hard to implement auto partitioning algorithm. This code here shows how we implemented auto partitioning for our experiments. We first created instance of sublayers on the meta device, which allows to create model without allocating tensor storage, but we can still access things like the tensor shapes, the D-type, etc. Based on this info, we can partition accordingly and then directly allocate tensors on the destination device. More specifically, we put all the layers instances into a list, and then we calculate the threshold as the total number of parameter values divided by the number of stages. And then we pack these layers in stages in order. Finally, we convert the list of stages into NN sequential module. This is very simple auto partitioning algorithm and works for our use case. And you can build your own more advanced versions depending upon your scenarios. We are working on building an automated version so that you don't have to build your own algorithms in future. Pipeline and DDP can seamlessly work together today. You just need to wrap the pipe model with DDP instance and leave the device ID argument empty. DDP will figure out the devices automatically. The figure shows what happens when we combine pipeline parallelism with DDP. We call it PDP. Suppose each pipeline spans two devices, and on top of that, we have two DDP processes. So there are 4 GPUs in total. Chunks here equals to 3, so there are 3 micro batches per mini batch. Each distinct color corresponds to 1 micro batch. We can see that it feeds the first micro batch to first GPU, and then the first micro batch moves over to the second GPU. It can then feed the second micro batch to the first GPU. So that way it can keep both the GPUs busy all the time. And then when the backward computation finishes for all gradients in one DDP bucket, the DDP will kick off all reduce or AR in this graph to synchronize gradients accordingly. Next, let's look at the memory saving techniques to reduce the model footprint needed for large model training. First common one is activation checkpointing. The model is organized into multiple blocks, and you wrap each block with a checkpoint wrapper. Within each block, the wrapper will discard activations after the forward pass and then recompute accordingly before the backward pass. So we only need to materialize activations for one block at a time. And the right side here shows the code for this. Next memory saving technique is activation offloading. It will offload the activations to CPU memory after the forward pass and then load them back to GPU memory before the backward computation. Compared to activation checkpoint seen in the previous slide, the first difference is that using different trade-offs to reduce peak memory consumptions. Activation checkpointing pays more computation to save GPU memory, and activation offloading pays device to host and host to device communication to reduce the GPU memory. The second distinction is that they also apply to different activation tensors. The activation checkpointing applies to activations within a checkpoint block, while activation offloading applies to activations outside of the checkpointing blocks. The technical reason here behind this design is that checkpoint wrapper can easily access other activations as they are outputs from checkpoint wrapper in the NN module, while the inner activations are in kind of a black box. So we just get rid of the entire autograd graph for the block and then rely on garbage collection to free up the memory. The third memory saving technique is parameter offloading. It is similar to activation offloading but applies to the model's parameters. It simply offloads parameters to CPU memory and then loads them back on demand before the computations. It can be further combined with FSDP to further reduce peak memory consumption, which can be useful for super large models. So we have talked about three training paradigms, DDP, FSDP, and PDP, where DDP replicates the models, FSDP shards model storage but does not shard the computation, and pipeline parallelism partitions both the model storage and the computation, but then it uses more devices. We also talked about the three memory saving techniques, the activation checkpointing, activation offloading, and parameter offloading, where checkpointing pays more computation to save memory consumption, whereas offloading pays more for device to host and host to device communication. There is another memory saving technique called micro-batching. It comes relatively with pipeline parallelism. It may not be obvious why micro-batching can save memory, as it does not help with activations or parameter memory savings. In addition to the model parameters, gradients, and activations, there are also temporary tensors allocated by the user program in the forward pass and by the autograd engine in the backward pass. This can be considerable amount of GPU memory and are usually proportional to the max batch size. Microbatching reduces the effective batch size as we are only computing one microbatch at a time on the device. So it helps to reduce the temporary tensor memory footprint. The figure shows the current cross-compatibility of training paradigms and the memory saving techniques. We are currently working on enhancing them so that users can pair them in arbitrary way to facilitate the different usage requirements. Next, let's look into the experiments and the insights. We tested these features using the min-GPT models with model sizes ranging from 100 million parameters all the way up to trillion parameters. We also integrated with meta-device to accelerate model initialization. Using FSDP, we wrapped each transformer layer into FSDP units for models below 81 billion parameters. For larger models, FSDP wrapped each individual linear layer to further reduce the peak memory consumption. We first measure the scalability by varying the number of GPUs. In this figure, the x-axis is number of GPUs and the y-axis is the throughput. Throughput is in terms of kilotokens per seconds and it is in the log scale. Different colors correspond to different training paradigms and number after each paradigm name is the batch size. The gray bar here shows the throughput of optimal scaling where we assume that there is no communication overhead at all. All pipelines in the experiment use two devices, so its input batch size is also 2x larger to make sure all experiments use the same per device batch size. There are three main observations from the results. First, the larger batch size leads to higher throughput, and batch sizes 20 is always more efficient than batch size 8 across all the paradigms, which is expected as larger batch size means more efficient kernels and lower amortized communication overhead. The second observation is that when scaling from 8 to 16 GPUs, there is a drop in throughput, and this is also expected because for 8 GPUs or below, it only uses a single machine, where communication goes through the 600 gigabits NVLink. For 16 GPUs, it has to travel via the 100 Gbps network. So basically, the cross-machine communication delay kills the performance. The drop is larger for larger models. And the third observation is that using multiple machines, PDP can outperform DDP. In this figure, it is more visible for GPT 2.7 billion one. You can see that the yellow bar is taller than the blue bars when using 16 GPUs. The speedup of PDP mainly comes from two sources. The first one, as we span each pipeline across two devices and it runs DDP on top, it basically breaks the global all-reduced ring into two smaller ones. And the smaller all-reduced rings run faster. From the figure, we see that the larger all-reduced ring with 16 GPUs on the top uses 18 milliseconds for each all-reduce. While using PDP, the delay drops to around 17 milliseconds. And second, as the two all-reduced rings span on two disjoint set of GPUs, they can run concurrently in overlapped fashion to further bump up the network utilization. From the figure, we see that each all-reduce takes 25 milliseconds to finish instead of 18 milliseconds times 2, which is 36 milliseconds. So these two together help to speed up PDP. In the previous slide, we mentioned that large batch sizes lead to higher throughput. We want to measure if that is always the case. We try to fit in as large batch size as we can for the different paradigms. PDP-2 is pipeline using 2 microbatches per mini batch, and PDP-4 is using 4 microbatches per mini batch. The x-axis is the batch size, and there are two y-axes here. The left one is the peak memory consumption, and the right one is the throughput. There are two observations here. First one, it is not always better to increase the batch size. The throughput can start becoming unstable when using around 80% of the GPU memory. This is because when operating near GPU memory capacity, it can lead to frequent defragmentation. And when the defragmentation algorithm kicks in, it will free all the CUDA cached blocks and try to allocate new larger ones, which will cause low CUDA malloc, and that will kill the performance. So we know that large batch size is better for throughput, but we need to keep the GPU memory usage below 80%. The second observation is that PDP-4 can fit in much larger batch size than PDP-2. This confirms what we mentioned before about microbatching, that it helps to reduce memory consumption of temporary tensors, and PDP-4 is using smaller microbatches. Next, we measure the model scale limits with different paradigms. The x-axis is model size and y-axis is the throughput. In the legend, the AC is activation checkpointing and AO is activation offloading. DDP starts to hit out-of-memory errors when model size is larger than 3 billion parameters for FP16 models. Another observation is that activation checkpointing and offloading significantly reduces peak memory consumption. This slide shows same experiments applied to the larger models. Two-device PDP starts to hit out of memory with 16 billion parameter models, and by increasing the number of pipeline stages, PDP can scale up to around 35 billion parameters for FP16 models. With 100 Gbps network, PDP outperforms FSDP on larger models as long as they can fit in the memory. Today, different clusters might use different network interconnect with various network bandwidths. We also want to know the impact of network bandwidth on training delay or throughput. So we measure 8 GPUs on one machine versus over 4 machines. The former uses 600 Gbps NVLink and the latter uses the 100 gigabit Ethernet. We compute the ratio of these two throughput and plot them. The left figure uses batch size of 8. We can see that speed up ratio steadily increases with increase of the model size. The ratio can be as large as 23x for FSDP when using a 6.8 billion parameter model. For larger models, speed up ratio drops. This is because we turn on parameter offloading to avoid out of memory errors. The ratio also drops when larger batch size as shown on the right figure. This is because amortized communication overhead is lower. Despite that, large batch sizes can still reach to 3 to 5x speedups. These two profiling figures can help to explain why the speedup ratio drops when working on larger models. The figure on the top shows the FSDP results without the parameter offloading. And we can see that the collective communication overhead dominates here. The bottom figure is when we turn on parameter offloading. It is clear that the device to host and the host to device copies introduce significant overhead, and collective communication is no longer the single source of delay. The H2D and D2H copies go through PCIe, and increases in network bandwidth won't help. That's why the visual drop can be seen. The profiling results also expose that there are many bubbles when doing parameter offloading, and we are working on optimizing this in the upcoming release. We also want to share the best practices we collected from our experiments. The figure shows which techniques can achieve the highest throughput for the different models and batch size combinations. For the left figure, we use the 8 GPUs on 4 different machines over 100 Gbps Ethernet. And on the right-hand side, it is for 8 GPUs on same machine connected over 600 Gbps NVLink. So the main difference between the two is the network communication overhead. From all the experiments, we found that the amortized communication overhead, the ACO, is a function of model size divided by the network bandwidth multiplied by the batch size. So when the ACO is low, less than 20 milliseconds per sample, DDP attains the highest throughput for models less than 3 billion parameters. When ACO is high, PDP achieves highest throughput for models less than 10 billion parameters. For the rest of the scenarios and models greater than 10 billion parameters, FSDP is the best option. And some additional best practices for FSDP. We recommend initializing the model on CPU and use the meta device for initialization. With bfloat 16 training, it can speed up roughly by 35%, and there is also a 32% memory reduction. With the backward prefetch, there is another 10% speed up. You can use the rank 0 CPU saving to avoid any out-of-memory issues during the large model savings. And use activation checkpointing as this speeds up large amounts of memory during the training. Next, we will dive into some of the best practices for profiling and troubleshooting large-scale model training runs. Large-scale model profiling and troubleshooting is hard, and the tools are still evolving across the industry. You will need to use a combination of tools like the Nvidia DCGM, Nvidia NSights, or the PyTorch profiler for profiling the actual training runs. Before launching your training job, due to the large number of GPUs involved in these trainings, you will start by running a pre-flight health check to verify the health of the cluster nodes. These are quick invasive tests that generally take a few seconds to run and are designed to verify that GPU is ready for training job and the NICL and the MPI network connectivity is working fine. While your job is running, periodically you will run post-flight checks using tools like Nvidia DCGM for background health checks that monitor the status of the training job. This will be very important when you are training like models for convergence, which can span up to 20, 30 days or longer. The epilogue health checks are medium duration invasive health checks when the job fails or health of the GPUs is a suspect. And the full system validation tests are long duration checks that are typically run for investigating hardware problems or other serious issues. We built the Prof experimental profiling and troubleshooting tool using the combination of NVIDIA DCGM and Prometheus. It supports Slurm jobs at present and with the AWS Parallel Cluster or the Azure Cycle Cloud. Grafana dashboards are built in and it provides details for the GPU utilization, which help identify bottlenecks and hotspots on the cluster. It also supports injecting errors for simulating GPU failure conditions using the DCGM policies and scripts. This includes tests for detecting the hardware errors like the ECC errors, the driver errors for the firmware errors, application-related errors like GPU semaphore timeout, the system's memory corruption like invalid corrupted push buffer stream, bus-related errors for the NVLink and PCIe, thermal and power-related problems where usage exceeds certain threshold causing performance degradation, and the frame buffer corruptions like invalid or corrupted push buffer stream. Here are a few screenshots of the dashboard and the health checks. You can see the utilization across the different GPUs, and you can see the hotspots and the thermal. These are some of the outputs for running all the prologue and epilogue tests. Let's dive into a quick demo. So what you see here is an output of the parallel cluster of training. You can see the different jobs and the details, CPU memory utilization. This is the S batch for executing this Slurm job. Seeing the output of all the pre-flight checks, the epilogue checks, and this is the job now executing on the cluster. You can see the output of the Slurm and the cloud init for launching of the nodes. Here is the training in progress. More insights about the actual job, including the network bandwidth, the output for the GPU nodes. You can see the NVLink and other details. This is the power utilization for the different GPUs. The memory utilization. Disk IO usage. The NVIDIA DCGM uses the DCGMI interface, and the profiling tools use the CUPT-based interface, which cannot be turned on at the same time. So when you need to turn on the job level profiling using the NVIDIA NSights or the PyTorch profiler, you will need to pause and then resume DCGM. This can be done using the command line or through the DCGM API. When you're training GPT-3 scale and larger models with 100 billion plus parameters, With hundreds of GPUs across multiple hosts, one often encounters 2 to 3 failures every other day. For this, you need to have good checkpoint and recovery mechanisms for job restarts. For best results, use a fast NFS-based storage and scratch device, such as the Azure or the AWS FSx cluster. Another thing to consider is to quarantine the bad nodes across the cluster. In the cloud, one of the recommended best practices is to have an extra 10 to 20 hot spare buffer capacity when you're running larger 100 billion plus parameter model training runs. What you see here is an example of the profiling code. So this is using the PyTorch profiler. So you can use it for profiling on a schedule. Certain parameters will need to be turned off when you're doing large scale training. For example, turn off the record shapes or the width flops as it results in seg faults at present, and we are working on solutions for this. Using the NVTX markers, you can do similar things for the Nvidia NSights by using the Torch Autograd Profiler emit NVTX. The PyTorch profiler supports single node trainings across multiple GPUs today. On-demand trigger for profiling is coming in H2 of 2022, and we are working on adding support for large-scale distributed training jobs. The Nvidia NSights supports multi-node, multi-GPUs. Here, on-demand trigger for the profiling on multiple nodes has to be handled by the users again at present. And you can find the example of this code in the link at the bottom. So this is what the Nvidia NSights multi-node, multi-GPU profiling looks like. And here are some screenshots from the PyTorch distributed training profiler. So we invite you to try things out. Check out the tutorials on the pytorch.org tutorials for distributed training. Go through our documentation and connect with us. You can connect on the GitHub by opening issues or connect on the Dev Discuss or the Discuss channels. And here are a few resources to help you quickly get started. So thank you all for listening in. Please feel free to reach out and connect on LinkedIn or through GitHub. I would also like to thank my colleagues, Shen, Yanli, Pavel, Rohan, Preetham, and others from the PyTorch distributed team that made all this work possible. Thank you all.